So we're continuing on with our shortest path algorithms. And we've been taking a look at the single source shortest path algorithm. And today we'll try to spend a little bit of time looking at the proofs. And we'll take a look at least at one of the proofs. And then maybe we'll come back to Dijkstra's proof, which is a little tricky. And then we will start by taking a look at the other possible shortest path algorithm variation, which was that of all pairs. Okay, and that was a little bit more expansive in the sense that we need to now take a look at the shortest paths, not just between any two pairs, any pair of vertices, but in fact, between all possible pairs. Okay, and we look at an algorithm called Floyd-Washall's algorithm, which essentially is based on dynamic programming. Okay, so the algorithms that we've been seeing so far are mostly greedy algorithms, and Floyd-Washall will be the first, perhaps, dynamic programming algorithm that we'll be looking at. So let's do a little bit of a review since it's been a little over a week since we last looked at this, and I'm sure that some of this is still fresh in your minds because of the midterm, but let's go through this anyway. So single source shortest path algorithm, we had the weights, and we had defined delta UV to be the shortest path weight. Okay, so if somehow you were able to figure out what the shortest path weight is, that would be called delta. And a shortest path from vertex U to V is then defined as any path P which has the weight WP is equal to the shortest path weight, right? And we had the following variations. So we've looked at the following three, and we hopefully shall spend some time looking at the all pairs problem. Relaxing an edge. So this is just a summary of some of the slides that we saw earlier, is that we're simply looking at, we're trying to say that if we have already have the estimates U and V between any two vertices, and if we've got the weight between those two vertices, then the relaxation process simply says, well, can we find a shorter path to the destination? Okay, so if you relax U, V, and W, essentially you're saying that, well, if this path is shorter, then we will reduce the destination length, otherwise we won't. So in the Dijkstra's algorithm, we saw that one of the shortcomings was that it doesn't work with negative edges. And I hope that this worked out all right in the midterm. And this was the details of the Dijkstra's algorithm, which we went over in the last lecture. And I'm not going to be repeating this stuff. And we saw that the analysis, the complexity was order of E log V, right? And the Bellman-Ford algorithm was the one which actually was able to handle negative weight cycles as well as negative weights. But in the case where you actually had a negative weight cycle, it simply returns a false. So I hope you got that right in the midterm, that example that I had actually a negative weight cycle. So it wouldn't return a true, it would return a false. Okay. And the complexity was order of V times E. Okay, so it's not as good as Dijkstra's complexity, simply because we're sort of doing a brute force approach. In the proof of correctness, we started off looking at some of the lemmas in the book. And the first one was the triangle inequality, and where we said that basically if you have an edge UV, and we have delta from S to V is the shortest path weight, all right, then it has to be less than equal to if you take any other path from S to U, and you add the path weight from U to V, then delta SV has to be less than equal to the shortest path weight to U, all right, plus the weight from U to V. And we said that, well, if that wasn't true, then it would be sort of a contradiction in terms. By definition, if this particular path was actually shorter than delta SV, then delta SV would in fact not be the shortest path weight, okay? And then the shortest path weight would be delta SU plus WUV, okay, by definition. So, so this is what is referred to as the triangle inequality. And then we have the upper bound property, okay, which basically says that we always have the estimate V dot D, the estimate to D, to be greater than equal to the actual shortest path weight from S to V. Okay, so because the estimates are initialized to infinity, they're essentially coming downwards. Okay, and obviously at some point they're going to come down all the way up till the actual shortest path weight. And so clearly this again is sort of kind of obvious. Okay, simply because the estimates are going to start off large and go down to be eventually they're going to hit the actual shortest path weight. And you have another property which is called the no path property, again kind of an obvious trivial thing, which is that in case there is no path from S to V, then the estimates are going to be infinity, and so will the actual shortest path weight, and that's by definition. So if there is no path, then the distance is infinite. And that comes in directly from the initialization. So now if we look at some other properties, so this is another lemma, which is the convergence property. And this is slightly more tricky than the earlier ones. And it basically says that if you have a shortest path, which goes from S to V. I think I would need to change the batteries, but I guess as batteries are all used up over here, I'll just try to speak louder. So if anybody has problem, please let me know and I'll try to speak louder. So the idea here is that if S through U to V is a shortest path, and you have is the shortest path in G for some U comma V, right? And if U to D is the shortest path, okay, so U is defined here as the last vertex before V. So you have a path going from source to some destination V. And we're saying, well, just the vertex, which is one vertex before the final destination. So U is the last vertex before V. So this here is an actual edge. This is not a path. So this is here a path. And eventually you have an edge which goes from U to V, which is the last vertex before V. And you say, well, if the estimate to this last vertex, U, is already the shortest path. Okay, so if the estimate to this last vertex, U, is already the shortest path weight to U, then if you relax the edge U, UV, then the estimate at V is now going to be the shortest path. Okay. So let me make sure that you guys sort of understand that. So essentially we're saying that you have this long path from U all the way to different vertices, from source to different vertices, you get to U, and that's the last vertex before V. Okay, and we're saying if the path to U, the estimate at U, is already the shortest path. Okay, and if we immediately after that relax the edge between U and V, right, then V's estimate is now going to become the shortest path weight. Okay, do people understand that? And if anybody can repeat that, if somebody understands it. If you, yes. Yes, so no, not one path, an edge only. So U is the last vertex before V. Okay, and there's only one edge between U and V. Yes. Okay, so let's say that you have another path going through some other vertex X, let's say, and this particular path is actually shorter. Okay, and so by definition, we're saying that this is a shortest path. Okay, so this particular path going through U and then to V is a shortest path. So by definition, if there is another path through X, it'll be equidistant or it'll be longer. It can't be shorter because this is defined to be the shortest path. Okay, so I hope that answers your question. Okay, so so can somebody try to repeat what this theorem, what this convergence property is actually saying in your own words? Yes. You got that a little wrong. So you had the initial portion partially right. You said that from source to U is the shortest path, but we're not just saying that. We're saying that that from S to V is the shortest path, and U just happens to be the last vertex in that path. See the difference? So we're saying that. So we're saying that S through U through V is a shortest path, okay? And U happens to be the last vertex before V. Which is a little different from what you said. You said that S through U is the shortest path, and then from U to V is an edge. But you didn't start with the assumption that S through V is going through U. Okay, so U is the last vertex in the shortest path. Do you understand the difference? Okay, can you see that again now? S to V, yeah. It's not a path, it's an edge. So U is the last vertex before V, and there's only an edge between U and V. So it's not a path. You see this line over here? That's a straight line. That's not a path. Okay, so U is the last edge in that particular shortest path. No. What we're basically trying to do in this particular lemma is that we're trying to prove a property. We're trying to state a property of the relaxation process. Okay, we're trying to say something about relaxation. Okay, so we're essentially saying that if you have this particular path, which is a shortest path, and you find U to be the last vertex in that path before V, okay? And if we've already found that the path to U is the shortest path, okay? Then by relaxing UV, then V's estimate is now guaranteed to be the shortest weight path. Okay, so it's sort of saying something about the relaxation process. All right, so saying that if you've got this long path and you've got till the last, the last component, and you figured it all out, all right, and then as soon as you relax the last edge, then the new estimate at the destination is now going to be, is guaranteed to be the shortest path weight. Okay, so this takes a little bit of time, but it's important to be able to understand this because this is critical in the proofs. Okay. Can somebody else give it an attempt? Try to say it in your own words. It's a bit of a challenge, but think about it. See if you can repeat the basic concept. Somebody's got to come up to the challenge. No? So you have this path, all right? You've got U is the last vertex before V. That means there's only one edge between U and V, okay? The estimate at U is the shortest path weight. Then if you relax between U and V, then the estimate at V is guaranteed to be the shortest path weight. Okay, so I don't think I can say it more frequently, but take a while, figure that out, and it's a fairly straightforward property of the relaxation process. Okay. So moving on, so the convergence property essentially can be expanded into the next lemma, which is the path relaxation property. Okay, and this becomes critical in proving the Bellman-Ford algorithm. Okay, and this basically says that let's say that P is a particular path, is a shortest path, and it comprises of all of these vertices now. Okay, so it's going from V0, V1, all the way up to Vk, and these are all edges now. Between V0 to V1 is an edge. So these are not paths. Notice that these are straight lines. These are all edges. Okay, so you've got a standard path and comprises of a whole bunch of edges. Okay, and we're saying that we have all of these edges which comprise the shortest path, and then we're saying that we're going to relax each one of those edges in that particular order. Okay, so we're going to relax V0 to V1 first, all right? Then we're going to relax V1 to V2 next. And we're going to go all the way in that particular order until we get to the final vertex Vk. All right, so we've got a long path comprised of edges. We relax each one of those edges in that particular order, all right? And if that happens, then it's guaranteed that when we finally relax the last edge, then the estimate at the final destination is going to be guaranteed to be the shortest path weight. Okay. So think of a simple example. Let's say we're going from from A to B to C, and let's say through D. Okay, so this is a shortest path, all right, from A to D. And we're saying that we already have the shortest path, okay? And now we're saying that if these are relaxed in this particular order, then the estimates after we've realized, if we've relaxed in this particular order, the estimate at the final destination after we've done this relaxation process is guaranteed to be the shortest path weight. Okay. And this is also true if you also have intermediate relaxations. So if you go through, if you relax this first, and then let's say you relax another path, and then you come back to this, and then you go through this. So you could go through other relaxations as well. All right. It is still guaranteed to be the shortest path weight. The final estimate is still guaranteed to be the shortest path weight. Okay. Yes.
You talk about
Let's say D goes to E. Okay. Sorry, B goes to E, and then E goes to C. So yeah. Yeah, sure. Yeah, so essentially what we're saying is that if you relaxed in this order, one, so let's say one, edge 2, and edge 3, then after relaxing 1, 2, and 3, the estimate at D is guaranteed to be the shortest path weight. Okay. Now, if you happen to do B and you happen to do number 4 in between, okay, so you did relaxed edge 1 and then relaxed edge 4 and then relaxed edge 2 and then relaxed edge 3. Once you get to 3, you've got an extra step over here. But once you get to, you relax edge 3, the estimate at D is going to be the shortest path weight. You've just done some extra steps, okay, and that doesn't change anything. All right. So if you think about this, and you think about the Ford, the other algorithm that we looked at. How do you see that working out? So can you see the two of them? So I'm going to go directly to the Bellman-Ford algorithm, and can you now see this as relating to the proof of Bellman-Ford? How do you see this path relaxation property, this lemma, sort of fitting in with the Bellman-Ford proof of correctness? Remember, in Bellman-Ford, we said we're going to do a brute force relaxation, okay? And the first round, we're going to relax all of the vertices, all of the edges, sorry. And the second iteration, we again going to relax all of the edges. And we're going to keep on repeating that until we've covered a certain minimum number. And that minimum number was the number of v minus 1. Okay, so how do you see these two sort of connecting, and can you see why the path relaxation property can help improving the Bellman-Ford? And let's see if somebody has a suggestion over here. So Bellman-Ford relaxes every relevant sequence, and the path relax property says that as long as we relax the edges of the shortest path in the sequence, then it will accumulate the shortest path. Okay. Yeah, sort of right, but I would appreciate if somebody can say it out loud rather than just typing it out, because it's a little easier to follow when you're describing the situation and perhaps looking at this particular example. So here is an algorithm which we saw earlier, and this finds out the shortest paths using the Bellman-Ford algorithm. And essentially we're saying that can you use the earlier path relaxation lemma to be able to prove the Bellman-Ford for correctness? Yes. Exactly, exactly. So did everybody follow? Can I get your name? Anna? Did everybody follow what Anna just said? Can somebody else repeat that? If you followed it? Yes? Yes, exactly. So one of them, so the first time you do the iteration, you're obviously going to hit, you're going to hit all the edges, which is a brute force method, but you're also going to hit the shortest, in the shortest path, you're also going to hit the correct vertex, okay? And the second time around, you're going to hit all the edges, but you're also going to hit the second edge in the shortest path, okay? So it's a really, it's a sledgehammer approach, and it sort of guarantees the whole process, okay? So essentially, this is what we're saying, is that in the first iteration, if V0, V1 is on the shortest path, that along with all the other edges is also going to be, it's going to be relaxed, but V0, V1 will also be relaxed, okay? In the second iteration, all the other edges are going to be relaxed, and it doesn't matter which order you do them in, but the second edge in the shortest path, which is V1 to V2, will also be relaxed, okay? And so on. So essentially, by doing it V-1 times, you've essentially guaranteed to find out the shortest path, okay? So hopefully that wasn't too bad. That's the extent to which the proofs, there's no probabilities over here. So it's a little easier perhaps as compared to some of the earlier proofs, yes. So what happens when you have negative? Well, if you have a negative edge versus a negative path cycle, okay, now let's think about that. It's a good question, okay? So let's separate out those two cases. Let's assume that you have, in the first case, you have negative edges, but you don't have a negative cycle, okay? And the second case, you have negative edges, which result in a negative weight cycle, okay? So let's look at the first case. The question is, in the first case, will the Bellman-Ford algorithm actually work? And what happens in the second case? So remember that it's going to have a response, which is a Boolean response, okay? So the Bellman-Ford algorithm has, it has the, it returns a true or false, but also returns the parent, the parents as well, indirectly. So can you sort of try to address that issue? What happens if you just have the first case? Will that work? And will that return a true? Why would you say that? So it'll continue on. And if there are no negative cycles, then after you've done V-1 iterations, and you do the Vth iteration, which is over here, okay? You do the extra iteration at the end, it's not going to result, and if there are no negative cycles, it's not going to have a further reduction in the estimates, okay? So, and if you don't have any further reductions in the estimates, that sort of indicates that you're done, okay? That you don't have any negative weight cycles. But if you do have negative weight cycles, then you're going to have some further reductions, okay? You're going to go down that infinite black hole, keep on going further and further negative estimates. And that's when you're going to realize that, okay, you've got to stop over here. And after V iterations, you're going to stop, okay? Because as soon as you've done the Vth iteration, you realize that, the relaxations are resulting in further reduction in estimates, then you've got a problem, okay? And you won't keep on going forever, and you're going to stop. So it's a good brute force algorithm, but if you imagine that you don't have negative weights in your graph, would you want to use this or Dijkstra's algorithm? which one would you prefer? Yeah, Dijkstra's naturally, right? Because in terms of the complexity, it's better. And this is, this is V times E versus the other one was E times log V, right? So this is much more complex, and you wouldn't use this unless you had negative weights. Now, Dijkstra's algorithm, to prove that, is a little tricky. And I'm going to throw a couple of slides at you. I want you to think about this and see if you can figure it out. It's got a whole bunch of steps which rely on the properties that we've talked about. And I'm not going to immediately attempt this. I just want you to sort of slowly look at this, and I'll give these 2 slides to you. And I want you to think about it, and we can come back to this. Okay, it's a little lengthy, and it's not immediately obvious as well. All right. So I'm going to just let that be on in front of you for a few seconds, but we'll come back to this. Okay, because it's a little tricky. So now let's talk about the all pairs shortest path algorithm. Okay, and this is essentially, the last one that we're going to look at as far as graphs are concerned, and then we'll return back to some of our favorite probabilistic algorithms, right? So here's the Floyd-Washall algorithm, and basically says, well, we're going to consider a graph, and we're going to allow negative weights. Okay. So it basically is saying, well, let me go back over here. So we said that you could solve this particular problem in the kind of naive way. All right. You already know how to do single pair shortest paths. So all you need to do is to find, if you want to do the all pairs, you could just repeat that V times, right? You could repeat that, making the source, change the source for all the V vertices. And if you had an algorithm which could do it, for example, Dijkstra's algorithm, all you need to do is repeat Dijkstra's algorithm V times, all right? And that would give you, some nice complexity, whatever complexity you had earlier, you would simply multiply that by the number of vertices, okay? However, Dijkstra's algorithm was great without negative edges. The second algorithm, Bellman-Ford, is also great if you have negative edges, but the complexity has increased. And if you want to multiply that again by V, the number of vertices, then the complexity again becomes quite unsurmountable. Okay, so we're not going to use either the Bellman-Ford or the Dijkstra's algorithm over here, and we're going to come up with to see if we can do a little better using a completely different algorithm, and that relies not on a greedy approach, but on a dynamic programming approach. Okay. And does somebody remember what dynamic programming, how that was different from the greedy approach? We sort of briefly covered that in one of our earlier lectures. What is the basic difference between the greedy approach and the dynamic programming approach? Anybody remembers? So in the greedy approach, okay, did you have a response? Yeah. Yeah. Overlapping, yeah. But there's something else that I perhaps mentioned in dynamic programming that you didn't mention. I don't know if I mentioned it or not. Well, if you remember one of the algorithms, and you have a tree and you're trying to compute the Fibonacci's, all right? And you're saying that if you did a brute force approach to Fibonacci's, you're computing Fibonacci of, let's say, 10, and you're using Fibonacci of 9 and 8, right? And then you're recomputing that. And when you're doing Fibonacci of 11, then you're doing Fibonacci of 10 and 9, right? So you're sort of repeating Fibonacci of 10 again. And then when you're doing Fibonacci of 12, you're going to recompute Fibonacci of 10 and 11, right? So dynamic programming would do it how? How would you change the Fibonacci algorithm so that you could use dynamic programming on that? I don't know if I've mentioned that or not. Okay, so let me explain that again over here. So let's say you're computing Fibonacci of X, and for that you need to compute the Fibonacci of X minus 1 and X minus 2. And then when you're computing the Fibonacci of X plus 1, you're going to use the Fibonacci of X as well as X minus 1, right? So now you can see a clear problem. Yes. So, yes. So essentially what you're saying is if you need to be able to use some of the past results, okay, you need to use this past result over here. How could you do it? Yeah, you'd have to store it somewhere. So yeah, so essentially it says, well, what we could do is use more space. Okay, so we could store all the past results. In this particular case, it's actually quite trivial. You don't really need dynamic programming because you could just store the last two. Okay, but in general, if you had a problem where you want to use all of these past results, okay, not just the last two, but you want to use all the past results, then you could use extra space, all right, and create some kind of a table and store all the past results. And every time you want to compute a new result, you would look up whether it is reusing some of the past results. And in that case, you would simply take the past result and plug it in. Okay, so in other words, you would store the Fibonacci of X minus 1, all right? And when you're computing the Fibonacci of X plus 1, then you would simply use X, which would have already been computed, or perhaps this was new, but X minus 1 was certainly already pre-computed. Okay, and if it's that stored in a table somewhere, you could just pull that out and plug it in. All right, so that's the basic idea in dynamic programming, is that the greedy approach if it doesn't work. Okay, if the greedy approach works, then you'd use a greedy algorithm. But if the greedy approach doesn't work, then what you could do is use a dynamic programming approach, and that does require those two properties. But in addition, what you're going to use is additional space. Okay, you're going to store all the past data, and you're going to sort of pull them out of a table and use them as and when necessary. Okay, so this is what we're going to see in this particular algorithm. If that's a new question or not. Okay, so dynamic approach, remember subproblem solutions to reuse them. Yeah, so greedy always takes the logically optimal next step. Yeah, all right. So let's take a look at how we're going to solve this problem. And we're going to look at how Floyd-Washall works at a high level initially, and then we'll try to see if we can look into why it works subsequently. Okay, so we're saying that the weights can be negative. All right, so in this case, this should be better than using Dijkstra's algorithm 3 times, right? Because Dijkstra could have worked, but Dijkstra doesn't work with negative weights, edges. Okay, so we're sort of making it a more general problem. And hopefully this algorithm should also be able to identify if you have a negative weight cycle, then it should also be able to tell you that there is a negative weight cycle, and you've got to stop at some point. So let's take a look at this example, which is from CLRS, the 4th edition. It's kind of a complex example, although I would have preferred a smaller example, but I think because this is something that you can refer to in the book, it is perhaps still has its merit. Okay, so we're going to start off with weights being defined. Okay, and we're going to define the weights as 0. Obviously, when you're going from from yourself to yourself. So this is the matrix, the weights matrix, which we have all the vertices on both of these columns and rows. So this is going from 1 through 5, 1 through 5. These are the 5 vertices. And you have the following weights. So the weight from 1 to 2 is 3, as you can see over here, and where there is no edge between, let's say, 1 and 4, then you identify that as infinite. Okay, so these are the edge weights as opposed to the distance weights. So we start off with the weights matrix, and then we're going to make a couple of changes. So first of all, we're going to define a distance matrix. Okay, so the distance matrix will have the same size, and it will be initialized to be the weight matrix. Okay, so the distance matrix and the superscript over here 0, I'll explain that in a few minutes. So we'll define the distance, the initial distance matrix, simply to be equal to the weight matrix. And the distance dij is simply the distance from, let's say, I to j. Okay, so we're saying that the distance d2 comma 4 is currently equal to the weight from 2 till 4, which should be the weight from 2 till 4, which is the weight 1 for that particular edge. Okay, so I hope you understand the distance matrix. We're going to also define a predecessor matrix, which again can be a little confusing the way it's been defined, but that's how the algorithm has been defined, and we'll go along with that definition. So it essentially says that we have predecessors for every vertex. Okay, so to go from 1 to 2, all right, so 1 to 2, there is a direct edge, as you can see over here. So the predecessor is 1 itself, kind of obvious, all right? Similarly, if you want to go from 1 to 3, you have a direct edge and whose weight is 8, all right? And so the predecessor to go from 1 to 3 is the vertex 1 itself. And where you don't have a direct edge initially, the predecessor is defined to be nil. So going from 1 to 4, there is no direct edge, so the predecessor is defined to be nil. Okay. So hopefully so far so good. Now let's go to the basic concept in the algorithm. So it essentially says that we're going to select an intermediate node, k. All right, so initially let's assume that you have the distances defined between I and j, and you know them. All right, initially know them to be direct edges, but at some point those are going to comprise of paths. And if you know the distance between dij, you're going to try to improve that by comparing it with an intermediate vertex. Okay, some intermediate node k, and you're going to simply say, well, is the current distance from I to j, is that as good or worse than if you went through the intermediate vertex? Okay, so if you went from I through k and then from k to j. Okay, and so you already have the estimates from I to k, you already have the estimates from k to j. So can you improve this particular path instead of going directly between I and j? Can you improve it if you went through k? Okay, so again, a fairly straightforward concept. So let's see how this plays out. So now what we're going to do is we're going to, in an iterative manner, we're going to go through all of the vertices. Okay, so initially we're going to say, well, if we went through k is equal to 1, okay, if we went through vertex 1 for all of these pairs, can we improve the weights? Can we improve the total distance? So let's see if we can do this. Can somebody try to fill this out? Okay, so looking at, let's say, 1 through 1. Okay, so can we improve the distance from 1 to 1 while going through 1? It's kind of an unnecessary question. Well, first of all, the distance from X to X is already 0, and you can't do better than that. Okay, so these are all going to be initially 0, and they're going to hopefully remain 0. Okay, and the question is, can you go from 1 to 2? Can you improve the distance from 1 to 2 by going through 1? Again, you're starting at 1, so you're already at 1, so you can't improve by going through 1. Okay, so this will also not change, and I'm going to show this by just a straight line. Okay, so obviously you can't improve going from 1 to 3 by going through 1. So all of these are going to remain unchanged. Is that clear? Okay. Similarly, going from 2 to 1 while going via 1 is kind of a silly question to ask. So all of these are also going to remain unchanged. Okay. Why? Because the first row and the first column will be irrelevant to go through, because k is equal to 1 in this case. All right. So the interesting question comes up when we look at this case over here. Okay, so let's take a look at going from I is equal to 2 to j is equal to 3. So can we improve the distance going from 2 to 3 while going directly from 2? Well, not necessarily directly, but whatever result we have so far, can we improve that by saying that, well, can we go through 1? So in other words, we're saying we want to start at 2, I is equal to 2, and we want to end at j is equal to 3, and we want to go via k is equal to 1. Okay, so can you go from 2 to 3 to 1 to 3? Is that possible? 2 to 1. Well, you're going to use the existing results. Okay, and the existing results basically say, well, if you want to go from 2 to 1, there is no current path. Okay, and it's infinite. Why? Because 2 to 1, currently there is no single edge, there is no path. Okay, so going from 2 to 1 to 3 basically says that 2 to 1 is infinite, and 1 to 3 has a cost of 8. Okay, so 8 plus infinity is infinity. Okay, and by the way, when you do implement these algorithms, then you have to make sure that you're not getting into overflow problems, right? So if you've defined infinity, for example, you're defining infinity to be the largest integer that's possible with 32 bits or 64 bits as your integer size, and then you add something to it, you've got to make sure that your implementation doesn't give you an overflow error. Okay, you've got to make sure that you're doing the infinite calculations properly. That might be a little tricky. So 8 plus infinity is again infinity, and the current cost to go from 2 to 3 is also infinite. So is infinity better than infinity? Well, I guess not. So this remains unchanged. Okay, this only changes if you find a better path. Okay, so this will not change. And as we're going through this, we can also make the changes in the predecessor path. Okay, so I'm simply going to put a straight line over there, which simply says that none of these are going to change. Okay, so this is not going to change as well. So let's keep on doing this for a few times until you've got the hang of it. So let's say is 2 to 4. Can you find a path going from 2 via 1 to 4? And is that better than going straight from 2 to 4? So 2 to 4 currently has an estimate of, sorry, that's the predecessor. The current distance is 1, and you need to go through 2 itself. Okay, that's the simple edge. So will it improve if you go through 1? Okay, so let's try that. So now we're saying we're going from I is equal to 2. Okay, and we're trying to end up at 4. So 2 to 4, the current distance is 1. But if we go through 1, can it improve situations? Well, you've got a problem there because 2 to 1 doesn't exist. So in fact, this entire row is going to be irrelevant because there is no current path from 2 to 1. Okay. So let's look at something more interesting, and let me just skip over here and see what we have. So this is what we get after we do the first iteration. Okay. And essentially you can see that some of these paths weights will change. And let's take a look at a couple of them. Those are the only 2 that are changing. So we're essentially saying that if you want to go from 4 to 2, okay, so 4 to 2 was currently infinite. But if you're going through 1, so you're going from 4 to 2, okay, so there was no current path going from I to j from 4 to 2. But if you go through 1, k is equal to 1, then there seems to be a path. You're going to take this particular path and this particular path, rather edge. So that's going to be 2 plus 3, and that's going to result in a distance of 5. Okay. And so you're going to not only change the distance, but also change the predecessor. So the predecessor before getting to 2 is now going to be 1. Okay. So now notice that the predecessor is not the vertex following 4, but it's the vertex before 2. Okay, so it's the vertex before the destination. So that's how we're going to define the predecessor matrix. So we've discovered 2 shorter paths. So 4, 1, 2. We can go 4, 1, 2, and we can also go 4, 1, 5. So we figured out 2 shorter paths to go from 4 to 5, which were earlier both infinite. Okay, so we compared infinity versus 2 minus 4, which was minus 2, and we compared infinity with 2 plus 3, which was 5, and in both cases that was less than infinity. Okay, so hopefully that is quite obvious as well so far. It does become a little interesting as we go further down. So now let's take a look at what happens if you want to use vertex 2. Okay, so we've already found the following matrix, which is essentially saying that if we go through vertex 1, then we found these paths. All right, we found these predecessors and we found the shortest distance. And now what we're going to do is we're going to save those. All right, and as dynamic programming proceeds, we're going to use the previous results to see if we can find better paths. Okay, so now we are going to use the following 2 results, D1 and D2. So if you notice that the superscript over here is indicating the paths that the vertices that we've already used, and we're going sort of in an incremental manner. All right, so we started with 0, and then we said, well, can we find a shorter path via vertex 1? And now we're saying, well, is there a shorter path via 2 after having already done 1? Okay. So you can see that we do have some results over here. And you can see that if we go from 1 to 4 via 2, so let's look at this particular path. So we're saying, well, the earlier there was no way to get from 1 to 4. Okay, so we're going from 1 to 4, j is equal to 4, and we had so far used 1 itself, and now we're going to use 2, k is equal to 2. And so we're saying that 3 plus 1 is equal to 4. So clearly there is a shorter path, and the predecessor to get to 4 is going to be 2. Okay. So is that clear? And if so, let's try to see if some of you guys can work out some of these cases. So let's take a look at k is equal to 3. And perhaps some of you can give it a shot and see how we do. So how do we start? Which columns and rows of this distance matrix can we immediately ignore and say that, well, those are going to be the same? So we're saying, well, what's the shortest distance? Can we improve the distance between I and j, okay, I to j, while going through number 3, node number 3, where k is equal to 3. Okay, so remember this particular diagram, we're saying that we're looking at going from di to j, all right, while going through an intermediate node k. Okay, so we're adding k and we're saying, is this path better, or is this the sum of these two paths better? Okay, fairly simple question that we're asking ourselves. And so let's take a look at this particular example and see, yes, please. Okay, so let's remove the diagonals over here. We're going to remove. Okay. So that's particular row. Anything else? Yeah, vertical as well. Yeah. So we've removed that particular row and that particular column, and we've removed the diagonal. Okay, so slightly small problem to grapple with. Now, next, can each of you take a shot at one of these so that you get the hang of things? Somebody wants to do 1 and 2. So we're saying, is there a shorter path between 1 and 2? All right, I is equal to 1 and j is equal to 2 by going through k, which is equal to 3. Okay, yes. Yeah, so if you went through from 1 to 3 and then to 2, 1 to 3 is currently 8. Okay, so remember, you could use your obvious sense to look at the graph and to figure it out, but the algorithm is not going to be looking at the graph itself. It's going to be looking at the matrices. You've got to get into the habit, if you want to implement this and do some examples, you've got to get into the habit of looking at the actual matrices. Okay, so you're going to say, well, 1 to 3 has a distance of 8, okay, and 3 to 2 has a distance of 4. Okay, from 3 to 2 is a distance of 4. So 4 plus 8 is going to be 12. And if you go directly from 1 to 2, that has a distance of 4. So this is not going to change, right? And so, sorry, we were doing 1 to 2, got that wrong. So this is not going to change, and this is not going to change either. Okay, great. Somebody else want to give it a shot? Perhaps an example which does change. Can you see an example which would change? So we're going from, currently we're going from I is equal to 1. And we're saying, well, j could be the, we've done 2, j could be now 4. I is equal to 1, j is equal to 4. Can you find a better path through k is equal to 3? I is equal to 1, j is equal to 4. And can we find a better path to 3? Anybody? How would you do the comparison? What would the comparison values be? This path versus this. So I going from 1 through 4 would be 1 to 4. Did I have the earlier one right? I just erased it, but in any case, that didn't change. But now we're saying I from 1 to 4 by going through. So currently the distance is 4. Right, 1 to 4 is 4. And going through 3 would imply that you go to 3 first. That's an 8. And 3 to 4 would be a 5. So 8 plus 5 is a 13. And so hopefully you got that 4, we already have a shorter path going directly. Okay, so that hasn't changed. Can anybody see a shorter path through 3? And if so, we can figure that one out. So we're saying, well, you're trying to go via 3, and maybe there is a shorter path. Is there one that exists? I can see one. Does anybody else? Yes. Sorry, 4 to 2, exactly. That's the one I was looking for. So can you tell me what the comparisons would be? So let me just erase this and see if we can do that over here. So we're going from I is equal to 4 to j is equal to 2, and we're going through k is equal to 3. So can you give me these numbers? -5, and that's a +4, and 4 to 2 currently is 4 to 2 is currently 5. Is that right? Yeah. So you notice that 4 to 2 currently was going through 1. All right. And by going through 3, it's found a better way. Okay. And it's using up the previous results. So it didn't say that, it didn't compare this particular route to the original 4 to 2, which was infinity because there was a direct edge, but compared it to the recent result. All right. And the recent result basically said that, yes, we have found a way to go through 1, which is shorter than infinity. All right. And then it compared the new shorter path to the best paths that we already had so far. So that's the whole concept of dynamic programming. You simply use the previous results, which you've sort of saved, and then try to use an algorithm which can help you improve things. Okay, so here are some of the results that hopefully I got that as well. So 4 to 2 is now -1, and 3 to 2 and 4 to 2 was earlier 5. And so now, so what would be, I've shown that to you, but what would be this particular value over here, the previous index? So we're going via 3, all right? So this one is a simple case, 4 to 3, all right? That's the only intermediate node. Let's take a look at another example. Okay. Let's see if we can do this. This is a little bit more slightly different, but pretty much the same thing repeated. So, and I've got certainly a particular example for you to work on. So can somebody do this? Is the distance between 3 to 5? So you're going from 3 to 5. Okay, and and you're comparing that to 3 to 4. K is equal to 4. And you're saying, well, is there a shorter path going via 4? Okay. Yes, somebody else. Other people to think as well. Somebody else want to do this one? Nobody else? Yes. Is what? Is 11, right? And you reading that off from the table, which is good, because you can see that there is no direct path from 3 to 5, but we had earlier found a way to go through, I believe, 2. Okay, so 3 to 5 is currently 11. 3 to 4 is currently 5. And from 4 to 5 is -2. So you have a result which is you're comparing 3 with 11, and clearly 3 is going to be better. Okay, so can you now trace the particular path that we've actually got from 3 to? So what was the original path from 3 to 5? 3 to 5 was originally from via 2, and how did you read that off? Because you saw that 3 to 5 was via 2. You had this as a parent index. All right, so this was the original path. Okay, and now you've come up with a different path, and that is 3 to 4 to 5. And what is that path now? Yeah, so 3, so now you have 3 to 4, right, which has a total distance of 4 plus 1, which is 5, all right? And from 4 to 5 is what? Is through 1, yeah. So now, so you've got a double hop, all right? So in other words, instead of going from 3 to 2 to 5, which was the original path over here, now we've got a better path, which is 3 to 2 to 4, bless you, and 4 to 1 to 5, okay? And that seems to be better, right? So the weights, can you tell me where would we enter the new weights for D and pi as well? So we'd go up to 3 over here and 5, and we would improve 11 over here to be 3. All right. What about this particular value? Should be 4. Predecessor. Okay, you're saying that the predecessor to get to 5 is now 4 because you're going this way, right? But think again, the predecessor is the previous vertex to get to 5. Is 4 the previous vertex? It's 1, right? Because you notice as you go through this path, it's actually 1. So I think that it should be right. Okay. So you get the idea that you're going, so the predecessor matrix, yes, I don't know who raised their hand first. Okay, what's the question? Instead of what? The K value? So you're saying that in the predecessor matrix, instead of keeping track of the predecessor vertex, if you keep track of K, which, so the predecessor matrix could be done in different ways. And I think there are multiple solutions to it. It's just that how has it actually been used in the actual algorithm, okay? And you could come up with a different predecessor matrix, which could actually not be a predecessor, but could be the next step, which is what I actually found more logical, all right? So if, for example, if you look at, if let's say we're trying to get from 3 to 5, okay? We're trying to get from 3 to 5. How is the predecessor matrix actually working? Okay, let's just figure out how this is working before we actually get to your question. So how would you actually find out the shortest path if you want to use this predecessor matrix? Okay, you were trying to get from 3 to 5, and it says the predecessor to 5 is, sorry, the wrong graph, yeah. So here is the actual matrix, okay? So this is the predecessor matrix, and we're saying that, so to get from 3 to 5, we've said that you actually need to go through 4, okay? To get to 3 to 5, you're going through 4 through a double up, okay? And there is an intermediate node from 3 to 4, which is actually 2, okay? And between 4 to 5, there's also an intermediate node, which is 1, okay? So as you're going from 3 to 5, it's saying the predecessor is 1, okay? Because you're actually following this longer path. Okay, so this is the actual path that you're following. And in order to get to 5, the predecessor is 1. But then how do you get to 1? So can you use this this matrix to sort of figure out the path, which is not completely obvious? Yeah, so you would say, well, how do you get to 1, right? So you say, well, 3 to 1, the predecessor is 4. So you see yourself, see how we're making our way backwards, right? So we said 3 to 5, the predecessor is 4. Now to be able to get to, the predecessor is 1. So to be able to get to 1, the predecessor is 4, okay? To get to 4, the predecessor is 2. To get to 2, the predecessor is yourself, okay? So that's how the predecessor matrix is actually working in, how it's been implemented in the actual algorithm in CLRS, okay? Which is a little tricky, okay? The other way that you could have done it is you could have said, well, I'm going to keep track of not the predecessors, but I'm going to keep track of the next hop, okay? Which you could have come up with your own algorithm, which could have said sort of, well, does that work or not? Well, you could say, you could sort of define that and say if it works. So we sort of run out of time. Let's, well, we're pretty much done, but we'll come back to some of the other aspects.